Hello, and thank you for joining me on this guided project. Today we're going to be using an LSTM. It's a regression prediction, so kind of think this is still like spreadsheet data. The simpler way, kind of regular data, classical tabular data, to do a linear regression prediction with the LSTM and some dense layers and some architecture that we'll build together. So first thing doing, just mounting into my drive. You can see the original data set from Kaggle right here. I chose this data set for predictions. I mean, I really like Google. My students would know that. I'm a big fan of Google, but and they're actually the ones really kind of behind the TensorFlow library as well. So, but I did this prediction because they have lots of rows on the scale data set, and this is a problem usually with stock market predictions. Uh, there's not enough rows, really. Truthfully, I've been working on a personal project for a long time, and there really just truthfully is not enough rows. There's only so many days that have happened. Anyway, so here just importing pandas, NumPy, TensorFlow, Seaborn as SNS, Matplotlib, PyPlot is PLT, and then we're going to use standard scalar here as well. But it's important to scale your data. Okay. So I have this data set saved in my GitHub reservoir. So you can just download it right directly from the site. This is the raw file version of this regular CSV file at this link. So you can just use this. And so if you just go read_CSV, this will work right off this website. So just like as if you were taking the file path from your computer, and so you don't have to worry about getting the data. It's already ready for you. So the first thing I like to do, just kind of inspect the data, is df.head. Really just make sure it is exactly what we were expecting. This looks exactly like we'd expect. We have our days, one day represented by each row. Okay. We're going to look at the shape of the data set, and we have 4,431 rows and 7 columns, and a really decent sized data set for a stock market prediction. Truly, it's hard to get even a few thousand rows. It's pretty challenging. So here what we're going to do is we're going to, for the EDA, I always like to use different than the standard colors. So I define a palette, so palettes, and it's a list of different palette colors. I go to colormind.io, define data sets, and I if you go to my Facebook page, I have this everywhere there. So and what I'm going to do here is I'm going to go for feet in df columns, the list of all the column names. I'm going to go, when we select that feature, when we select that column from the data set, if the data type of that column, so D type, is not equal to an object, then I'm going to go SNS dot hist plot, and I'm going to go palette, just like the first position from my palette right here. So just index 0 and do the palette. So run the palette first, and then we'll run this little loop, and then we're going plt.show to print out the plot at each run. So that kind of comes out nice, and we can see we have an exponential distribution for all of these, exponential like distribution for all of these plots here, which is very common in a financial distribution. Come from the finance world. I still hold my CFA, and it is quite the exponential is a big problem in financial type data. So every data type kind of industry has its own kind of feel to it. Anyway, so here we're going into the MACD. Don't worry, I did not expect you to do a lot of programming here for the indicator development, but we're going to use these indicators as predictive measures in our model. So kind of the historical time series of different representations of the price to predict today's price. See how good we do. Kind of classical technical trading was based off this type of concept, so this should work. So here in this first one, we're just going to do exponential weighted moving average span of 12. So EWM, and taking the mean of those. And then here what we're going to do, we're going to take the 12 minus the 26 period. This is the fast MACD. We're then going to take a span of exponential weighted moving averages. Here, span of 9 of the fast one for the slow, and then we're going to do the fast minus the slow to get the final indicator. So a few steps here, teaching you some financial math as well, but just it's actually quite simple once you know what you're doing. It took me a few tries to get it right the first time. So here we just added the exponential weighted average, an indicator based around that. Here, I left this one a little bit more complicated to do. This has to do with how much it's moved, relative strength index, how much it's moved in relation to its relative past. So this is just kind of using the rolling average as well as the max and min values to kind of give a sense of how many positive up and how many positive negative days and how big were those movements to develop this indicator. So we go there and let's take a look at those two indicators right down here. And we see we get two different representations of the price. They're more or less stationary. So these will be good for us to make predictions with. We also need to make our targets stationary. So a good way to do this, especially with financial data, because if you just take first differences, those also will not likely be stationary because Google stock, let's say, is growing, but everyone always expects 10%. So it's always expected to grow 10%. And then that means the change is also always growing. So percentage change is a better thing for financial data. And so we're going to take the percentage change of this data set, and we're going to assign it to a new column. And what we'll do here, just to check the null values, so we should have quite a few null values now. So is null, we did an indicator develop that needed so many days to build it. So we should have some null values from that, and then as well from the percentage change feature. So here we have is null, just to inspect this, dot sum parentheses, and then we get a sum of all of the true null values. So here we see we got 14 right here. We're going to engineer some time features. Just to be conscious of those null values, we'll come back to them in a second. So we're going to engineer some time series features here. We'll make a list of 0 to 1. This could be fun for you to experiment with, and this will be engineering of these two indicators in the past to predict today's price and really see if we can learn patterns from the past to make our model work. So what we're going to do here, we run both of those lists. We'll make those two lists. We're going to go for D, just to keep it nice and short, for D in days max. So these are the days in the past. We're going to go then days max, or colon, and then we're starting our for block of code. For none, well, not none, for day, and this is an F string, so this automatically put the variable number in here. So we'll have column names with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 day ago. And then we're going to do this to the MACD column, and we're going to shift it. So we actually have to move this data frame so that it's in the same row. So we do create a new row here, but we have computers that are pretty fast. So we'll do that for the MACD and the RSI as well. So we're creating two of those. And this, again, would be really fun to play around with. This is how I built my time series data set using kind of this, using time series analytics, going a step further and deciding on which pattern of the past historical days could be good. So something fun to play around with. I certainly am still playing around with it to try and predict the stock market. So there we go. And we see here we got a whole bunch of new features. So just looking into the MACD, both of those right here. So we see that they're shifted 1, and then we would expect them to be for all of them as well. So we're going to drop here all of the null values that were created by a data set. As we know, there are some, and this is not going to work for a model. So we're going to go drop NA and equal to DS. So we'll drop any row that has a null value, and we know there's only like 14 of those. Next, a good thing, or something I like to do, is create a list of our features that we're going to put into our model, just to give us a lot of control of what's going really into our model. So we're going to go df.columns, and then you can just select right here from this list, go to MACD's 1, copy those, and then copy the close percent change for the target right here. That's already done for you because I'm a nice teacher. And here we're going to do a split index. We have lots of rows, so we're going to do 4,000 as the train, and because time series we have to do historic, or it's best to do historical, and then use the most current days as our testing. So here we're going to do a time series split. So just we're defining, kind of more historical to train that, because we really want to predict the future. So we want to see how good history is at training the future. So a little bit different than the standard sklearn train test split, but for working with the time series data set. So, and then just checking here all of our null data sets, or just to make sure there's no null in our data set here. So we create these two columns up above here. So we have features and target. So what we can do is select those, put them in the list, or put them in the first set of square brackets, and select out the list, assigning it to train, to X train, and Y train using the target list, the list of the one feature that we're going to use here. We'll put that right here. Okay. We'll then print out the shape of each one of these. Get a good sense of both of these. And let's run this 2 cells. And there we go. So we got 3,000. We did less than 5. So it's less 3,995 rows and 470 test sets. So we're going to then standardize. So we'll take standard scalar. Oops. So it's first none spot, standard scalar. And I love Google Colab. It's easy autofill. And we might as well fit this as we load this up because might as well. So this scalar we're ready to use, we want to do what's learned from the training set to scale the test set, because we won't know, technically have never seen the training set, so we can't really use it to learn what the mean and what the standard deviation is for the scaling process. So we have to doing it this way. It just ensures that we're not kind of any data leakage from the test to the training, just to ensure as much as we can our model's predictive. So here we're trained our scalar, and we're going to go standard scalar dot transform. And then we'll do transform as well on the test sets. And here, so we're putting the test set in this in the parentheses right here, and then we're going to be returning that test set as well. So running those two, and then we're going to get the dimension to use in the model down below of our train to get really how many columns we have in our data set, and then we'll make it organic with what happens above. So let's do our architecture. So I find it really good just to set and define kind of lots of the stuff that happens inside the model all in one place right above. So here what we'll define is the tan-H activation for the, ALU for the dense layers, tan-H for the recurrent. I always find that works better on recurrent, and ALU is one of my favorite ones just for the dense layers. Here for our loss function, we're doing 500 epochs. We're doing a learning rate of 0.001. We're doing a loss of mean absolute error. And we're going to use an optimizer of S, so capital S, capital G, capital D. Okay, so let's build our model together. Okay, so here we're going to define a sequential model, and we're going to define this into the model model object here. So we're going to go layers, tf.keras.layers dot LSTM, so long short-term memory. And here we'll go 13 units, recurrent activation. And so here what we're going to do is we're going to put a recurrent activation right there, that right there. Okay. And then what we're going to do is dense. We're going to do a dropout layer right here. And we're going to drop out 20% of layers. That really helps prevent, really important for preventing overfitting. We're then going to do a dense layer right here, and then we're going to give it an activation of dense activation. Okay, let's do that. And then the last layer, we're doing a regression prediction. So we're just going to define a dense layer with one neuron. That's going to be our output. Okay, so then we're going to compile the model with the loss of above, which is mean absolute error, our optimizer, which is stochastic gradient descent. And if you want to look at the mean squared error, you could do metrics equals mean squared error. And that kind of messes up the plot, so I didn't do it right here, but if you want to select, okay. Here what we're going to do is we're going to define the history is equal to the model, so we can inspect the history as we go through. We're going to fit the model with our X train, Y train, and TR, just a little bit easier to write. We're going to do a validation split. This is for money, so you got to train on as many rows as possible. So we're going to do a 2.2 split so that we save as much for training as possible. Our epochs are going to be our attribute up above, EPS, which is 500. And we're going to model, we're going to do a batch size. So this should change pretty fast. We're probably going to time warp this video forward, but let's train this. Let's run these cells. Model's not defined. Oops. Oh, and spelling mistakes. Silly things gotta go slow. And there we go. We define our layer. And make sure layers. tf.keras.layers. Definitely done that before. And here we're fitting our model and assigning it to history. Epochs. And so a little spelling mistake here. Epochs. And that's why I have EPS. Epochs. So we'll train our model. So we'll go pretty fast. And I will see you when this model is done training. Okay. So our model is finished training. It was actually really not too long. And we used a big batch size here. I'm using Google Colab, so I can use a bigger batch size if you wanted to use 128 or 256 or something. Just in case, this is a little bit hard for your computer, but this makes it go really fast. This is how many rows are being processed at each time, right? So it just makes it faster if they process more. And here using a GPU, really it doesn't take any longer to process multiple things at the same time, which is the benefit of using them for training your neural network. Okay. And so here we'll just do, I really love this technique for doing the plot of the history. So we're going to go pd.dataFrame. We're going to put our history object into a data frame. Then we're just going to use pandas plot to plot the palette. And we're going to give the color of the two palettes. Get a nice little printout here of the loss and the validation. This is a little bit different than your standard, what you'd expect from a standard plot, but remember we did a time series separation, so the relationships of variables and how they interact with our target tend to change over time, and so really you can see there's almost a continuous change from the two time periods of how we were able to predict with our features and stuff. So and this I would say I've seen this quite a bit in time series type splits, and so here we'll just do one last thing and do our model.eval and doing our two test scores. And we see we got an error of 0.015. And the percentage chance we were able to predict kind of relatively an average error of 1%. So I would say it's not so bad. But again, there are some caveats that there's the error in the percentage change. So really, again, you have to kind of analyze that. You're almost kind of good and not good. I wouldn't say this is going to get you predicting anything in the stock market, but maybe one day. Who knows? Thank you for joining me on this guided project, and I will see you for the next one.